Okay, cool. So, welcome everybody to our tech talk. Basically, if you haven't get the chips, feel free to just come and grab some chips. Feel free to grab it in the middle of the talk. Anyways, these are your dinner. Okay, so be alert that this talk is gonna be kind of like intense on math and physics, but you don't have to worry about it because well, it also took me a whole year to finish this project, and I'm also gonna talk a bit about why we're having this tech talk. Like anyways, so I have a slide for that actually. Why tech talk? The reason being, a lot of the senior members are graduating, okay, and we want to pass on the knowledge, and there's some attempts on like trying different ways. Like we had some I don't know, like just any attempts that we failed, and we found that probably there should be a better way to pass on all of these knowledges. And also for tech talks, this is aiming all the sub-teams, meaning whether you're from like algorithm, control, mechanical, electrical, you're all welcome to attend the tech talks, even though it's not focused on your own interest. And this is because when you're designing a robot, you have to learn about all aspects of the robot. And like for example, when you're doing some mechanical designs, you have to care about like how wiring is going to happen, and how is it going to affect control team, how is it going to affect algorithm team. So for example, if you're designing a, say, gimbal system, mechanical team is going to care about, okay, I have to draw a gimbal system that's going to shoot very accurately, and I have to control the, we call it the launching latency, which is when you get a signal from the algorithm team to fire, and when I believe all of you guys have already seen the speed detector, which is the mouth of the robot, it detects whether there's a projectile launching from the mouth. And this period of time should be, so there's basically a latency for sure, but we would have to make sure this is, within a reasonable range. And this is especially beneficial for our algorithm team when they're doing auto aiming, because you would have to predict what's going to happen in the future, like 100 milliseconds. But if it fluctuates too much, the prediction will no longer be accurate. So this is not what, like if you're from algorithm team, you definitely need some help from the control team and mechanical team. So learning all the aspects of the robots is definitely going to help you when you're designing your own algorithm or when you're drawing CAD and so on and so forth. And to encourage you guys actually to like take notes, let's say, we have, at least for this lecture, I would guarantee you a position to pilot the robot on November game if you send me a markdown note of what we're talking about today. And if it's accepted, you're gonna be the pilot. So like again, this is gonna be math intensive, and don't worry about it. When I was a freshman, I was so confused what to learn. I'm an ME, by the way, and in ME we learned all the aspects. We learned fluids, thermal, control, like everything, just a whole mess. But having the opportunity to see like what's gonna happen in your career in the 4 year in Purdue is really gonna help you. So if you see some like unfamiliar terms or just some concept that you haven't met before, take it easy, because I also didn't understand it. But it's gonna give you an opportunity to see what's gonna happen and what to expect in the lectures. Because I really have no idea what the differential equation was when I took the differential equation. So yeah. Okay, and some upcoming projects, we're gonna have topics like, this is called basically PMP, which is it perspective endpoints, correct? Okay, so it's basically when you're taking a picture, you want to know, like from this 2D image, you want to know a 3D coordinate of what exactly is happening in the graph. And you do this by a specific transform system. And there's dedicated functions in OpenCV, but we're gonna dig into details of this function or something. And on the right side is the forward for algorithm team, where you can see like they took the input from the camera, do some detection, do some classification, and then predict some result using Kalman filter, feed it back to the PMP solver to get a pitch and yaw axis and send it to the control team to actually control the cable. And these all look very abstract, but you should expect these upcoming projects to come. And BoilerBot, which is our former electrical lead, and his nickname in Discord, I believe, is Electric Freshman or something. And he's gonna talk about supercap. Okay, you can see on this field, the green bar on the bottom is the super cap, and it allows you to move like very fast. And it's kind of hard to see from this first person view, but I have a second link over here, which is the game with UW and VT last year. And you can see the red side, they go like crazy fast to the reload zone. And imagine that you're having a face-to-face battle, and you would have to go back to reload your ammos and get your HP. Saving that 2 seconds is really gonna save your life. So this is all because of the super cap system that allows you to draw that extra amount of power from the battery. And which means this is a very crucial topic, and BoilerBot is gonna talk about these topics. And yeah, and oh wait, I forgot to show this video here. Oh yeah, this is the a demonstration of the auto aiming system, and I think this is also played on the call. Is it? I have no idea. Yeah, but you can see there's a camera mounting on the gimbal system, and it's actively tracking the target as it translates and rotates. And yeah. Okay. And there's also some upcoming projects or topics covered by mechanical teams. And this is just a okay, this is a purely mechanical gravity compensation system. I think most of you guys have seen like robot arm that does the gravity compensation, where if you move the end effector at any places, it's basically gonna hold its position and not gonna move. But that's because of the control algorithm. This one is purely mechanical. You can see that spring, they did a whole lot of calculations and analysis, and they come up with this mechanism. Yeah. So these are some upcoming projects or topics we're gonna cover in the Tech Talk series. And by the way, we named this series what's that again? Behind the Build. Yeah. Just fun fact. Okay. So let's get started. We'll let Adam go. So before this, I would like to do a little thought experience. So if I have this Apple Pencil and I hold the tip, and then I just drop it. This is called the free response of the system. So if you care about the location of the tip, you can get a graph kind of like it's on the top, and then when I release it, it goes down. This is called a free response. And can anyone tell me if this is a stable system or unstable system? Unstable, okay. So theoretically, this can be a marginally stable system. Like, meaning if I just put the Apple Pencil here, and I make it like extremely balanced. And if I let go without any disturbance, without any like breath of air, it's gonna stand here until there's disturbance and it becomes unstable. And if you want to stabilize this system and like control the height of this Apple Pencil, how can you do it? You can move your finger and track like, basically, there's something happened with your eyes. You get the picture of this Apple Pencil and you see it's tilting over, and then you give it an input to push this way, right? And then you can stabilize this system somehow. And this is kind of like a quick demonstration of what feedback control is. I believe a lot of you guys have experience in maybe FRC, FTC, or VEX. You guys probably have heard of that PID controller and implement a whole lot of that. And that's a very good example of a feedback control where you get some sensor inputs of any kind, and then you manipulate your system in some way to stabilize or control it in the way that you want. And if you want me to like paraphrase what control team does, I would say we are trying to stabilize unstable system and control it in the way that we want. And so let's get back to wheel-leg balancing robot. The first question we're going to answer is why we want a wheel-leg robot anyways. Because we already have the 4-wheel robot. We also have a, I don't know if you guys have ever seen our previous balancing robot where there's 2 fixed wheels on the chassis. It's also, like it also satisfies the balancing chassis requirements in the rule where you guarantee to have 2 armor plates, which is a huge advantage, but we are still hoping to have this wheel-leg balancing robot. Why is that? So here's a little demonstration. So if you have a robot, right, and if the you're happy basically, you're having this little wrench on your top. This is my 4 demonstration of a robot arm. And if you want to move forward, what's going to happen is you tilt forward, which makes the platform no longer stable. And we don't want that to happen, especially in industrial applications. You want your working platform to be as stable as possible. So what it means is that you're going to be no longer happy. And if you introduce another degree of freedom at the hip joint, like here, it allows you to stabilize the platform in a way that the pitch angle doesn't move. Then you're going to be very happy. Okay. However, if you take a look at this kind of terrain and you want to stand on it horizontally, meaning you're sitting like this, what's going to happen is you're tilting, like you're basically flipping over, and you're going to be mad. What can happen is if you introduce another degree of freedom to allow you to extend and retract your leg, you can again stabilize your platform. So these are 2 perspectives to take a look at this robot, where you have these 2 degrees of freedom that allows you to stabilize the platform no matter what kind of terrain is under you. So you're gonna be, I don't know how to describe it. It's so stupid. Okay, now be very alert because we're gonna start to have a lot of math starting from here. And if you want to get that pilot position, take your notebook or your iPad and take notes. Okay, the first question I'm gonna ask is what kind of mechanism is this? So, for example, I have my arm, and basically this is like a 2-bar linkage, and specifically an open loop 2-bar linkage, because it has 2 bars basically. So my question is, what kind of mechanism is this? Is it closed loop? Is it open loop? Or how many bars does it have? Yep.
Is it a 4-bar?
Is it a 4-bar? Is it a 4-bar? 1, 2, 3, 4. Is it 4-bar? Any other answers? 5-bar? Why?
Because you told me.
Okay. Actually, that's right. it's a 5-bar linkage. And if you take a look here, these two motors are rigidly connected. It doesn't have to be a form of a rigid arm. But in some applications, these some movable joints are rigidly connected. We also consider it as a rigid bar. So this is basically a closed loop 5-bar linkage mechanism. So we are having two closed loop 5-bar linkages on both sides, where allows us to have more degrees of freedom to be more adaptive to different kinds of terrain. Now, how many DOF, which is degrees of freedom, does this one 5-bar linkage have? We're specifically talking about the end effector of degrees of freedom, meaning just assuming that this bar is fixed. How many degrees of freedom do you have? 2? Any other answers? Okay, so if you think about it this way, in a 2D plane, because right now we're only looking at the 5-bar linkage. If you only look at this 2D plane, how can this point move in the space? It can move to up, down, which is 1 degree of freedom. It also moves to left and right, which is, it kind of resembles the Cartesian coordinate system where you have, when you're defining a point, you have x and y, right? So you guys are right. It's a 2 degrees of freedom, 2 degree of freedom mechanism. And I believe most of you guys have heard of polar coordinate system, where you have a mapping between the Cartesian to the polar, where how you define it is you have an angle and the length of this point. So it is all with respect to a fixed point, where in this case we're considering the fixed bar in the chassis is stable. So with that being said, your end effector can move in 2 directions, or in another sense, it can move away from the chassis, it can move back to the chassis, and it can rotate with respect to chassis. So, okay, I'm gonna have a hard time erasing this. Okay, so you have this these 2 motors, which is actuating this 5-bar linkage. And if you think about it in another way, that whenever these 2 motors are applying some torque, you are having a torque which is virtual, that is controlling the rotation of this 5-bar linkage, and a pushing force downward to adjust the height from the chassis to the bottom wheel. So 2 different ways to look at it. The first one is physical, which is T1 and T2. These are the physical 2 motors up there, which are constantly applying torque. But another way to view this is you would have 2 virtual torque or forces that is going to apply at the center of the 2 motors that controls the rotation of the 5-bar linkage. Another one is the pushing force downward to control the up and down motion of this leg. Okay, is that clear? Okay. Now we're gonna get into some very intense mathematics and physics, but I'm gonna give you guys the answer first. That because intuitively, it's very hard to think of T1 and T2. Like if you think about what degree of freedom it's controlling, you can hardly describe it. The only thing you can tell is T1 is controlling the thigh of the 5-bar leg, the upper leg, and T2 is also controlling the upper leg on the right. But it doesn't really tell us a whole lot about how this is going to affect the system. On the other hand, if you take a look at tau and F, you can clearly imagine what's going to happen if you have these torques and forces. So for example, if you have an F, you can imagine that the wheel is going to be pushed outward or like further away from the chassis. Whereas if you have tau, you would have this whole 5-bar linkage mechanism to rotate like back and forth. But it's very hard to map T1 and T2 and give some like physical like degree of freedom that you can imagine. So in this case, we're gonna have some kind of mapping to allow us to work with tau at F. And then the J here, this is a transform matrix that's gonna map these two torques and force into T1 and T2. And after that, you would only have to think about this whole problem in the task space, and then you compute what's going to happen for the two motors, basically. Okay. So just to be clear, I think a lot of you guys are freshmen here. I don't know if you have ever exposed to linear algebra, but the notation here is T1, T2 equals to J times tau and F. So another way to look at this is you would have A1 tau plus, let's just say B1 F, and A2 tau plus B2 F. Okay, so you have this linear combination of tau and F, and then you calculate what's going to happen for T1 and T2. And be aware, this is it's not guaranteed to have this linear relationship. Sometimes this relationship can be non-linear, meaning you may have a little square on top of the tau, or you may have like sine, cosine, or any non-linear function you can think of. But to like, most of the time we linearize things to make things easier for us. And I'm gonna prove this, and like at the end of the proof, you're gonna see this is a exact solution, meaning there's no approximation. Because it turns out that the mapping between these two vectors, T1 and T2 and tau and F, is indeed linear. Okay, so I'm giving you the result first, just because you may get lost like in a few seconds because there's going to be a lot of math. Okay, to get started, we're going to prove a property, and I name it linear velocity projection equality. I don't know how, there's probably already a name for this, but I just can't find it. But this is what it's about. So if you have a rigid bar, any shape, you have 2 points on this bar, A and B. This rigid bar is moving in the space in any form. So if I throw this Apple Pencil, it's going to have a linear velocity and a rotational velocity. But at one instance, and you take 2 points on this rigid bar, you can have the velocity for these 2 points. Now, we draw a vector from A to B. This is guaranteed to exist at all times because you're having a rigid bar. The bar doesn't deform or anything like that. This is a rigid bar. So you're guaranteed to have a fixed XAB. Now, the property we're going to prove is the dot product of VA and XAB is equals to the dot product of BB and XAB. Let's pause here and think about it like in an intuitive way. What does it actually mean? So, for example, if I have this Apple Pencil and I just move it in a space like this, what is essentially happening at the moment? If you take 2 points on this Apple Pencil, if you think about it, it kind of makes sense that along this Apple Pencil, the 2 points are having the same linear velocity. So if you're standing, like, imagine you're standing on this pencil, and then I'm moving like this. It kind of makes sense to you that these 2 points are moving in the same, like, at the same velocity. And if you can't imagine that, it's okay, we're gonna prove it. If you cannot understand the proof, it's also okay. just remember this property, and we're going to use it to do a little bit of mapping between the two torques and the, like when we're talking about the 2 degrees of freedom, the fiber linkage have, we're going to use this property when we're proving that. But intuitively, these 2 points should also like move in the same linear, like at the same linear speed. Okay, now we get to the rigorous math proof, and don't be worried if you don't understand it, because you'll get there. So take notes in your math class, whatever you're taking to 161, 162. Pay attention, because that's gonna help a lot. Okay, we're gonna review a little bit about dot product. So if we're taking a dot product of 2 vectors, let's say vector A and vector B. The dot product is if you take the projection of A onto B, and then you multiply these 2 scalars together. So you're multiplying this one and this one. Okay, that's just a review. Okay. Now we're getting to the proof. How we're going to prove this is we introduce another point called R along the line segment on AB. And then we're going to say on this R, there's also going to be a speed. I'm sorry, velocity, because it's a vector. And then what we're doing is we also claim that this R is rotating at a certain velocity. Now, if you don't understand that, it's okay. This is kinematics for rigid body. It basically describes the velocity with respect to a point on the rigid body. So the velocity of A is equals to the velocity of R, which is like you can take it as like a base velocity, and then you project it onto something because you have a rotational velocity and a certain distance. It's kind of like if I rotate this pencil, the end is going to have some kind of linear velocity. So using this formula, you can get VA and VB, which is equals to VR plus the cross product of omega and XRA. I think this is covered in high school. Okay. Yeah. As I just said, like, if you don't understand any of these concepts, it's a good chance for you to first get familiarized with it, get for whatever, and then pay attention to your lecture, and you're gonna learn a lot. Okay, then we're gonna do a dot product on both sides, and this is gonna work because it's a dot product. It doesn't matter the order you multiply them. If you're using a cross product, then it might affect the direction and stuff. But here we introduce a dot product on both sides, and the equation should still hold. Now we're gonna expand this. So what's gonna happen is you are taking XAB into the brackets. The left side I just basically swapped them, and it's essentially the same because it's a dot product. It doesn't matter like how you project the vectors onto another. It's the result's still gonna be a scalar. The second on the right side of the equation, I put XAB into the 2 different terms. Right? Okay. Then we're gonna use a little property. The cross product of 2 vectors should be perpendicular to like any of these 2 vectors. Like it's like right-hand rule, right? Like if you have 2 vectors, then the result should be like perpendicular to it. And also the dot product of 2 perpendicular vectors should be 0. Okay. Using these 2 properties. Oh, by the way, an extension of the notepad. The cross product of omega and RA should also be perpendicular to AB. This is just because AR is on AB. Okay, then we can cross these 2 terms out. Because the result of omega cross RA is perpendicular to AB. and the dot product of these two is 0. Now you notice that on the right hand side, both equations remains vector Vr and vector Vr dot product with vector Xav. Therefore, we can equate the left hand side together, which proves the property on the top, where again, if I'm moving this rigid body and you have 2 points on this bar, the linear velocity along these 2 points, so the linear velocity of these 2 points should be the same, because like that's how you like project the velocity onto this line, and no matter how you move it, it's like always along line. Imagine you're standing on this pencil all the time, so it's gonna basically be there. Okay, is that clear? Any questions? Okay, so I'm assuming everyone already know this. Okay. What is this? Okay, now we're gonna introduce another concept called virtual work principle. It's kind of like the conservation law of energy, where I'm gonna explain it this way. So imagine you have T1 and T2, and then you move it a little bit. So imagine during like 0.001 second, you're applying this torque to these two bars, and it moves a little bit. This is gonna have some effects on F, which is our end effector, which is the point basically we really cares about. And this power should be the same if we think about it in the other way we just introduced, which is the tau and F. So what I mean is, if in this same instance, if you think about T1, T2 as tau and F, it should be essentially the same, where you apply tau to this fiber linkage and the whole mechanism moves a little bit, and you're applying this F, and the end effector moves down a little bit. And the power of these two should be the same, where you consider T1 and T2 as the input of the system. So in math, what I mean is T1 times D, I didn't define this, I'm sorry. D1 is basically the angle of the left bar, and D2 is basically the bar on the right hand side, T2, where T2 is corresponding to. And X is the corresponding displacement of F, and theta is the corresponding angle of tau. Yep.
Can you mark it on the diagram?
Okay. So T1, T2, and X. And these are all like very tiny displacement or angular displacement in this mechanism. So this is called a virtual work principle, where you would have some physical inputs. But if you think about it in some other way, where it covers all the degrees of freedom, and the way they move should also be the same. So yeah. Okay. Now, what we're gonna do is we take. We haven't get there yet. So we rewrite it in the matrix form because it's easier to manipulate as things move forward. And this is basically the same thing. And again, if you haven't taken linear algebra, it's totally fine. This whole form is basically just a neater way of representing the equation above. And then we're going to take derivative of the upper part. So what this means is basically you divide left hand side and right hand side with a dt, where I think most of you guys have seen something like d equals to dx by dt. It's essentially the same thing, where this is just, you're applying this in the matrix form. Okay, then what we're going to do is to rewrite the vectors into one letter. And this is only because it's easier to represent. And here you can already see the forms gets too closer to the result I showed you guys earlier, where I write T equals to JF, where we were trying to find the mapping between these two vectors, and here we're kind of getting there, but it's still not in the form that we want, so we still have to do a little manipulation to get to there. And how we're gonna do it is, okay, so remember this equation from the previous slide. So it's basically we apply the virtual world principle, and then we rewrite in matrix form. We take the time derivative, and then we rewrite this form just to be closer to what we actually want to get. And I'm putting the same equation up there. Okay, now the next step is we assume that this corresponding relation exists, where this J is just a mapping between omega and VC. Okay, and now we apply the equation into the mapping we already have, so we can get the equation above. Now, if we simplify things a bit, we can cancel the VC at the bottom. Now it gets very interesting because it's like really already the same form as what we assume to be. But the question right now is, this is just some, like, you guys don't have to care about this. This is just like some manipulation where it allows you to apply this law easier on the physical system, because you always want the transform matrix to be in front of the vector you want to transform. This is only because this is basically just how linear algebra works, and we want to get this nice mapping form that traditionally we have the J matrix in front of the vector we have. Okay, now we have this mapping, but the only problem is this is solely based on the assumption that we have a mapping between the angular velocity omega m and VC. Again, what these terms are, so we are basically trying to map V1, V2, these two terms with theta, and this x, I think. So we are essentially trying to find a relationship that connects D1, D2, and theta and x. Yeah, we like this is purely based on this assumption, and we have to prove that this relationship actually exists. Okay, it's gonna get more intense, and like this 5-bar linkage mapping is like kind of the most intense, like mathematically intense part that you have to get through, and this like why this mechanism is so complicated. One of the reasons is because this is a closed loop system, and closed loop system always get things like overcomplicate things because you always have that extra constraint and stuff. But yeah, here we are, and we still have to deal with it. Okay, remember we talked about the linear velocity mapping onto a rod, where you have VB and VC. So now we're considering VC as our rigid bar, and we have the 2 points that's lying on this rigid bar, which is B and C. Now we can say that the dot product of VC times XVC is equals to VB times XVC. And to get to what we want, remember we are trying to relate V1, V2 with theta and x. So we probably want to introduce the terms that we want to exist in the result that we end up with. So we expand VB into V1 dot cross XAB. And you can further expand vector XAB into a vector, where then you introduce the, okay, there's a typo. Yeah, basically it's just like one of it is cosine, one is sine, but just yeah. Okay, then you do the same thing with VC, where you try to introduce the L and theta into the term, because essentially you would want theta to be mapped with V1 and V4. So here we go. VC equals to L dot plus L times theta dot. And then you decompose it into two vectors. Now, if you plug those things in, also you can represent XBC in the same way, and it's essentially just some manipulation of the trigonometries. Then you plug all the things back to that equation on top, and you end up with this huge equation here. And still remember your goal. What is your goal? Your goal is to try to map theta 1 with phi1 with theta and x. So you can extract phi1 very easily because, as you can see, phi1 dot is only appearing in the very front of the equation. Then you end up with this nice matrix. Well, I wouldn't call it nice, but at least nice. It's something. Yeah. Okay. Now we have half part of it. Then we do the same thing with CD, where you have the 2 points on the rod, and you map the linear velocity onto the rod and claim they're the same. So essentially you're doing this. And I'm not going to write everything again, but essentially what you're going to get is you get a form kind of like this. And I skipped a lot of steps because I don't want to scare you guys about how this thing actually works. But essentially, the whole thing is about you applying that equity we proved, and then you're gonna end up with this mapping relationship to map FC onto TM. Okay, this is very intense, and this is the worst part. But the main takeaway from this is that right now, after we prove this, the way we think about this mechanism is no longer a 5-bar linkage. Rather, we can think of it as a bar like this, where it has a motor over here, and a linear motor that can apply some force along this rod. Because we have proven that T1 and T2 has a mapping, and it's also an exact solution that you can map tau and F with. Okay, so this is gonna ease things a lot for us because we no longer have to care about how this 5-bar mechanism work with each other, because as you can imagine, there's gonna be interaction forces at each joint, and we don't really want to care about that. And believe me, interaction forces are the worst forces you want to have in your model, and we actually have to deal with something that's kind of similar to this. Okay, now let's go back to this plot. And the first, we have proven that the 2 degrees of freedom has been decoupled to a turning torque and a pushing force. And they have the exact mapping to T1 and T2. So how are we going to use these two? We're going to start with the slightly easier one, which is the F. And as you can imagine, F essentially controls the length of the leg. By length, I mean the distance between the end effector wheel to the center of the chassis. And because tau really doesn't affect anything on this line. So really you're just using the F in this case. And I'm gonna introduce our leg length controller, where in this scenario, it's kind of easier to see. So imagine you are on an uneven surface, and if we abstract things a little bit, it's gonna be a slope where your robot is standing on there. And if you don't apply an active leg length controller, where you just set the leg length to be the exact number that you want, what's going to happen is it's going to basically flip over. So what we want to do is we want the platform to be horizontal at all time, where you will have to change the leg length a little bit. And it turns out the two length, the delta L1 and delta L2, should be the same, because Like if you think about it, it's like, if you take a look at this animation again, you are rotating about the center of this robot. So essentially the extraction and retraction, or extension and the retraction of the two legs, two-leg length should be the same. Okay. Now let's get to the control diagram of like how we actually want to control this. Like if you guys think about this intuitively, what kind of sensor should we use on this controller? Yeah, exactly. We need to use the IMU to detect what's the angle of this, and we want to correct this until the platform reaches 0. So with that being said, we have a plan, which is a fancy term for all the control engineers to use for the system you're controlling in, and they always call it a plan. And then you have your reference fee roll, which is 0 in our case, where we want the platform to be 0 at all times. There are some applications where you want to change this angle, like adapt, like I guess like in some tricky way. For example, if you're having a 1v1 battle, you're hiding behind the wall, and if you're having this real leg balancing robot, you can set this R fee roll to be like 10 degrees, and then you can just peek and hit your opponent. But basically, if you're applying the algorithm, it's essentially the same, but you need to have this reference. Right, so in our example, this reference is essentially 0. Then you will have this L target, and this L target is the length of the middle of the robot that we observe from the middle of the robot. So basically, what I'm talking about is the length of this double-sided arrow. And if you take this, and then you would have, you can think about it, you would have to use a sensor input to kind of like correct this angle to be 0. And how we do it is we feed it into an observer. That's also a fancy name for sensor. And sometimes you would have some like algorithm that deal with this. But essentially this is, we call it an observer, and it gives you the state of the robot, which in our case is the roll angle of the robot. And then you subtract it. I believe a lot of you guys have some experience in PID where you calculate the error, and this is exactly where error exists. And you get this error where you notice, okay, I want my platform to be horizontal, but because of something, maybe like you're standing on a uneven terrain, it makes my platform like uneven anymore. Doesn't make my platform even anymore. Then you would have this error, and then you feed it into a PID controller. And the output of this PID controller is going to be the amount of delta L1 and delta L2. Sorry. Okay. Then you will get the delta L1 and delta L2, and then you sum it up with the target. Then you can get a one of it is minus, one of it is plus. And because these two are essentially the same. I actually have to write L1 on top of there, but in this case it's the same. This is actually typo 1. But yeah. Then you get the actual leg length you want it to be. And then you feed it into another PID controller that compares it with the current height. And then you can calculate the F force, and then you can feed it back into the plane. And this F is essentially the virtual force that we talk about, where we map the T1 and T2, those two hip joints, into the middle one, the tau and the F. And the F is the F left and F right where we're referring to at this point. Yep.
So just to clarify, F left and F right are the control to your motors on the two on both sides?
Yeah, on both sides. On both sides, yeah. Okay, and this is the result. I think this is played at some events already. This is basically a demonstration of the algorithm, where when you lift it up, the sensor can sense the error and then applies a delta L into the two sides, and it's gonna change the leg length. And here you can see there's some steady state error, and this is because first the gain is not large enough where you still have this steady state error, and second is because I didn't apply integrator, which is the PID to the I term in the controller. And the reason being, after I apply it, maybe I can fine tune it a bit more, but I'm lazy, and it turns out it becomes a bipedal walking robot because it doesn't convert. It doesn't convert, and yeah. Okay, so that's for the leg length. Now, what left for us is another degree of freedom, which is the rotational degree of freedom on the top, where you have the flexibility to adjust the platform angle. And to simplify things, again, we're simplifying this model to a rigid bar, where we assume a fixed leg length and only one bar. Because we have already proven that the T2 and T1 can be mapped into the TB over here with the force that we just applied. And the reason why we can assume a fixed leg length is because we apply this leg length controller that we just showed, and we assume it to be perfect at all times. But in real life, it's never going to happen. And that will lead to some specific errors and stuff. But for now, to simplify things, just to give you a peace of mind, just assume the model that we're talking about is on the right-hand side, where you have the body on top, and the rigid bar, and the wheel. And be aware that although this is a very under-actuated system, the two inputs, meaning the two motors that we installed on this model, is the first one, which is TA, and that is the wheel motor, where if you apply the torque, it's gonna have a torque applied to the wheel. At the same time, it's gonna have a torque that's in the reverse direction on the bar, because this is a motor and it has again the reaction force, which we apparently don't want to deal with. But that's how that torque works. The same thing for TB, where when you're applying this torque to the bar, it applies a positive direction torque onto the bar. At the same time, it applies a reverse direction torque onto the body as well. Okay. So let's take a look at this. And what we're going to end up with is a system of equation that describes what's going to happen when you're giving this system a certain input. And using this system of equations, we can predict what's going to happen. And then we use some strategy called optimal control. And the specific algorithm we're using is called a linear quadratic regulator, which is LQR. I think probably some of you guys have already heard about this. This is just kind of like, you can think about it as PID. It's kind of like you have this model and then you apply some controller and it behaves in the same way that you want. But the main point here is we need to know what exactly is going to happen if we apply some input. Because later on we'll see most optimal control method relies on an accurate model. Okay, and the method we're going to use here is called Newton-Euler method, and which is essentially just F equals UMA. Very simple, but we're going to take a look at it very quickly. So the first component we want to take a look, again, all the arrows means forces. A, Y, and AX are the reaction forces between the bar and the wheel. Okay, so let's take a look at this carefully. We have obviously a friction force that is coming from the floor to the wheel. We have a support force that is also coming from the ground to the wheel. Then we have the forces applied from the rigid bar onto the wheel, which is AX and AY. And here it looks kind of weird because the rod is kind of pushing downwards onto the wheel, but the direction is going to work out with the math, so we don't really have to care about it at this point. But the main part we have to care about is, as I mentioned just now, all these torques and forces should be in reverse direction when you're applying to the other opponent. So let's get back to the wheel. The last term we haven't talked about is the TA, which is essentially the torque that's applied on the wheel by the motor. Then we have the bar, where you can see AX and AY are applied in different direction. TA is also applied in different direction. Actually, all these parts have gravity, obviously, but I skipped it on the graph. But please include it in your own graph if you want to draw this. And I was just lazy. And the gravity term is gonna end up showing in the equation that's gonna show in the middle later on. Okay. Bx and By and Tb, they work the same way as AX, AY, and TA. And finally, the body, where you have different direction of Bx and By, then you have the Tb over here. Okay. Then we basically apply F equals to ma. So we're gonna first take a look at the top right, the body block. So in the x direction, what you want to have is, okay, actually this let's take a look at the back. Then you can rotate this bar to be wherever it wants to be. And then you basically fix the theta. Now, the body can still move, so you basically just define another feet. Then after you define these three parts, you can completely define what the setup of this whole robot in a 2D space. So these, we call it independent variables, where they're independent with each other, while together these all three variables, we can define how this robot looks like in the space. And you may know the instantaneous setup of this robot at the moment if you know these three terms. But you wouldn't know if it's moving or it's accelerating or something. So to get more information, you would need to take the first order derivative, second order derivative, to get the whole picture of what's actually going on. So, but anyways, the main takeaway from here is the three very important variables that we use to define this robot can be defined in these sets of equations. And all of you guys have solved system equations. And the number of unknowns, if the number of unknowns equals to the number of equations, you get a solution. So if you look closely, the three independent variables with okay, let me start over. So what we don't know is what's going to happen for these three independent variables and the reaction forces like By, Bx, Ax, and Ay. It turns out we can solve these and then just keep the system for the three independent variables. And that way we can fully describe what is going to happen if we give it a certain amount of input, which is the TA and TB. Okay, this sounds very abstract, but if you're at ME, you're gonna learn this in I think ME 270. Yeah. And this is basically just one of the ways to model this. This is called Newton-Euler method. There are other methods, you probably have heard of Lagrangian or some other advanced method where they can neglect the reaction forces. Is it called reaction forces? Never mind. Just the Ax, Ay, Bx, By, that kind of forces, which kind of annoys me a lot. But again, Newton-Euler method is the most intuitive method where you just basically apply Newton's second law, F equals to ma, and you get these whole lot of things where we can describe this whole model. Okay, now we have this model. We have to make it in a form that is easier for us to use. Again, I skipped a lot of steps here, but the point that you should understand is that we use these terms to define what is going to happen to the robot. And what this is you can see the x, theta, and v here, which defines the setup of this robot. And the velocity describes how it's actually moving. And you can get an equation that is x dot equal to a x plus b. Where x, a, b is over there. And when you're after you have this whole system, sorry, this is u, where u is, this is a very bad slide. TA and TB. It's like if you think about it in an algebraic way, you actually can solve for x if you have all the numbers in the equation. Like that's a wrong way to perceive this, but like you can think about it this way if you haven't heard of state space formulation. But essentially, this is what we use to describe the dynamics of the system. And after we have this model, any questions, by the way? Yeah, again, this there might be a lot of concepts you haven't heard about, and the whole thing about this TED Talk is to just introduce you to some of these concepts, and you're gonna know what the other teams are doing. Also, give you some directions of what you would expect in your 4 years in Purdue. So, yeah, just yeah. Okay. Now we introduce LQR controller. I didn't understand this at all when I first looked at it, but I'm gonna try my best to explain things. So here, sorry. Okay. So here, the Q is the state penalty. R is the input penalty. So what this equation describes is that when you're applying an LQR controller, it tries to minimize the J, which sums everything up. And like, just get to understand this for now, just get an intuition of what's happening over here. So I'm gonna expand this equation in like a more easily understandable way. So if you have x, say we have all the x dot what is it? Theta dot d dot transpose. And Q here is a diagonal matrix where all the components except the diagonal components are 0. So what I mean is you can have something like 100, 10, 0.1, 0.2, 1,000, 2,000. While all these terms are wrong. But anyways, just like all the other terms are 0 basically. Okay. And then we have x. Yeah. Sorry. Oh, I just erased it. Okay, anyways, let's just assume you guys know what's gonna happen over here. I just write a whole lot of here. Okay, and then very small. What this whole thing I just wrote is going to equal to a vector. Actually, I really have to write this down. I won't be able to explain this. So I write this equal to x dot theta here you have 100, 10, 0.1, 0.2, 1,000, 2,000 times the same thing. And what this is equal to is it's going to be 100 x squared, 10 x dot squared, 0.1 theta squared, 0.2 theta dot squared, 1,000 v squared, 2,000 v dot squared. And again, the goal is to try to minimize this whole thing. So we want the whole thing, each component of this thing, to be as small as possible. What does that mean? You want all of these things to be small at the same time, while you have that weight in the front. So here you can see you have that like maneuverability to like say the importance of how you want these states to be. So for example, in this case, like I don't really care about what theta is going to be. Because even if theta is very big, the weight is 0.1. Whereas the weight for phi1, for phi is 2,000. So a little bit of fluctuation on there is going to cause a lot of cost, which is the J up there. So LQR introduced a very smart way to keep a balance of all the states we care about, and then it tries to minimize the error of all these states. So I hope this explains things a little bit. And the same thing happens here, where on the other hand, this is trying to parameterize your input. So this is a lot easier because it's just TA, TB. And let's say we have 10 and 100. And this is going to be a vector with TA squared, TB squared. What this means is that it's going to parameterize that if you have a very large TB. And why we want to do that, maybe our motor where TB represent is not powerful enough. So we want to set the cost to be very high. While TA might be maybe more powerful, and then you just set the cost to be lower. Then when you're solving for the equation, the optimal input so-called, you're going to get a relatively high TA. And the Q and R appears in the same J equation over here, which means the weight for the states and the input are in some way related. So if you don't care about the input at all, you can set these two to like 0.0001 and this to 0.0001. What you're gonna get is crazily fast response. So if you set the X target to be 10, so I want this robot to move like crazily fast to 10. Imagine you have a balancing robot and you're applying this LQR controller. You set the input as this. What's gonna happen is it's gonna speed up like very crazy and go to the destination you set it to be. However, if you set TA and TB, the weight for TA and TB to very high, what's gonna happen is it's gonna slowly accelerate and then slowly decelerate and it reaches the destination you want it to be. Okay, now I actually have a simulation for this run on my PC. I have to I'm gonna try to connect to my PC remote. Okay, let's. Now we're gonna demonstrate this a little bit. Before we do that, actually, let's go back to here to see what all these weight represents. Let's use this one. So in this setup, what kind of Q and R would you expect? Meaning like what are the states that we care about more? and what are the states that we don't really care about? Why are we introducing here?
We care a lot about feet because we want to keep it steady.
Right.
And we also care about X because we want it to be stay in place.
Yeah, exactly. Let me repeat what he said. So what we care about is if the platform is horizontal or not, and if the wheel is moving or not, because that's what we want. Like we want to move while the platform is stable. What we don't care, on the other hand, is the angle of the leg, because that's the whole reason we have this setup, is to use the leg mechanism to accelerate and decelerate. Which means we want to set Q for theta to be as small as possible while feasible, and set the cost for phi to be very high. Okay, so let's do the experiment here. This is kind of wrong because I was doing that experiment. So what we want to do is let's say 0.1 for theta. Okay, that's the leg. We want 0.1, let's say, and 200 and 100. Okay. Save. Yeah, okay, save. Come on. Save. Let me save.
Sorry.
Okay, whatever. I'm just gonna round the same image. It's gonna round. Okay, I'll unplug this and run this first. Okay, this is either. I'm gonna save this. And then I'll pull up the simulation. Then I'll run this. Hope it works. Okay, it works. If you're from control team, pay attention to this because this is gonna likely be your next onboarding project. And it's not gonna be like the second order, like with two inverted pendulum, but it's gonna be like one inverted pendulum basically. Okay. Now you can see, that leg is like providing that acceleration over there, that like it kind of moves back and then gives you that tilting angle for you to accelerate and decelerate. Let's take a look at it again. Pay attention to the leg. You see the leg is moving back to push things forward. Okay. Now let's try to change the Q value and see what's gonna happen. This is the block diagram, which is gonna be your onboarding project. It's not this one, like it's a lot simpler one, but it's essentially the same one. Okay, because I can't save it, I have to unplug this thing and change the value. Okay, so what I'm changing here, I'll change it first and I'll show you, is that I change the theta to be very high. We should probably have made that on the piece today. Okay. Here we go. Let's say we change this to 100. We change this to 200. And we don't care about feet. So let's just say 0.1. And here. Right. Okay, I'm just gonna plug it. I'll just for that. Run the simulation again. Okay. Now you can see like it's not the leg what's changing the position. Like it's right now it's like I put my head down and I accelerate and I raise my head up, which is not desired. This is why when you're setting up an LQR controller, the Q and R matrix is so important that you set the state that you care about to a very high value, whereas you set the for example the theta here that you don't care about to a very low value. Okay. Now let's get back to this. Yeah. And yeah, you don't really have to care about. This is just the solution of this optimization problem, where you can get the input, and then that's essentially what happened in the simulation. And it calculates an optimal input from the minimization problem of the cost, where you set the Q and R. Okay, and this is the result of like really not very important, but like the important thing about LQR right now is that how these Q and R fix the result. Yeah.
If you cared about like the acceleration of the system, could you assign like weights to that as well in the same state cost function? Does it only have to go with the initial velocity?
Okay, this is a good question. You cannot,
Okay.
because acceleration is not in your state, and you don't have the maneuverability of that state. Right now, you can only control x and x dot and how you care about these vectors, but how x double dot is going to respond is out of your control. You can observe it, but you cannot manipulate them.
So how are you manipulating both of those at the same time?
You mean x and x dot?
Yeah.
Yeah, that's like how. You remember when we set the Q matrix, you have those two diagonal. Yeah. Then it's going to calculate a optimal input and manipulate things in the way that you want, satisfying the requirement you're given that you want to minimize the cost for the ones you set to a high volume states. That makes sense.
Okay.
Other questions? Now, to get back to our 5R linkage, this is the result. This is the result after we apply that mapping where you have those two joined, the pushing force, the tau, that thing, to the model. And it turns out it behaves exactly the same way as our simplified model where you have that rigid bar. But right now you have the 5R, and then it acts the same way as the 2R. The only difference is that it's achieving this whole functionality with a 5R linkage. Now, let's recap a little bit and let's take a look what is happening over here. So you have this 4-bar, no, 5-bar, and then you can map the two torques on the top into T1 and T2. You map it into tau and then the F force. Then you apply the dynamic model using an optimal control method, and you tune a called cost matrix, Q and R, to get an optimal input. Then it lets the robot to balance itself. If you put things together, this is the control diagram where you apply Rx, the target states. You minus the state that you're currently passing into your LQR controller. It's going to generate two inputs, which is our TA and TB just now. TA is the torque that applies to the wheel. TL is the torque that applies to the linkage. And then you also get the leg controller that we talked about in the very beginning, where you have a PID leg, and then you get the force. Now take a look at this. We have TL and F, which is the 2 degrees of freedom that we talked about for the 5-bar linkage, and you pass it into the mapping J. Then you get TM, which is the T1 and T2 of the 2 hip motor at the joint. Then you're passing the wheel torque, hip torque into the plant, and it feedbacks the loop by getting in all the data we want from the observer, either sensor, encoder, whatever it is, to your reference, and then it completes the cycle. And it runs at like about 500 hertz or something, and then just, yeah. So I think you already seen a lot of the robots. I'm not gonna put demonstration video for that, but this one is a robot flying the ramp, and it actually lands, and it looks smooth because this is the only one successful case. And I make sure I crop this out very nicely. And but again, there are still problems with this model. If you take a look closely into this, especially observe what's going to happen when at the moment it lands. So when it lands, it kind of like merely stays stable, and this is because when it launches in the air, the model is no longer true. Remember, we talked about the no-slip conditions, that you would need the friction force to make this model a valid one. And then when you're in the air, the model is no longer true. So that's why in the air it behaves in a weird way, that when it lands, it kind of diverges and does not converge back to the stable state. And we would want to work on that to get a more accurate model, even when it's slipping or in the air. Another one is, we talked about we're using this 2D model, and this is problematic. Why? Oh, this is a big one. Yeah, it's kind of a mess. Like the battery just fell off on the robot. Oh. And yeah, it does. And this is because we were talking about a 2D model, and then we put things together on 2 legs. But it doesn't take care of any motion or effects in the 3D world. So on a highway, a high-speed way, the road is probably tilting inwards of the direction you're curving to. Is due to centripetal force. But 2D model, unfortunately, doesn't take care of that. That's the reason why it basically tilts over. Okay, so there's some like work on this robot right now to trying to get a 2D model of it, and it looks very abstract again. I barely understand this myself. It's ABC is the left leg, DEF is the right leg, and CF is the body. And then if you model this as, we call it full order dynamics, you could take care of the angular motion, and there's a whole bunch of stuff going on there. And in this case, it's going to be very hard to model this using the Newton-Euler method we mentioned, F equals to ma, because you can imagine all these joints, they have a lot of reaction forces, and you would have actually, I think, 33 equations, rather than the 9 equations, or 8 equations we talked about. And when I solve it in MATLAB, it gives me a result that's like even too long for the terminals to display, and like, so there exists like some method like Lagrangian to simplify things a little bit. Another thing is the velocity observer, where you can imagine, we talked about the state X we care about, which is the displacement of the wheel, and how we track it. If you think about it, it has to be the encoder, right? Because that's where you track the X position. But what happens if it slips? You would lose the reference to the roll frame, and your estimation of the X amount will no longer be accurate. And the way we deal with it is we use Kalman filter to fuse the IMU data with the encoder. Now, you don't have to understand what common filter does, but it basically takes input from two sensors and fuse them in some way that makes the measurement more accurate. And the model that we rely on, that we can talk about a little bit, is this one. So if you think about this, what happens here is V dot equals to A, which makes sense because V dot is equals to A. So this is called a constant acceleration model, where you assume the acceleration doesn't change rapidly. So think about when slip occurs, your acceleration is going to change rapidly because there's a slipping event occurring. So if you assume this constant A, you can get like a reasonably good measurement out of the encoder and IMU altogether. And here, again, there's some math getting involved there, and you should be able to get a good result after you do the calculations and apply it to the physical system. Okay, this is just a demonstration of what's going on. You can see the wheel's gonna lose track of the rolled frame as it goes on top of that rod. But it still stays balanced. And this is because it converges using the IMU data. This one is, I think you guys have already seen this before. But it can basically lose track of the roll frame, but it still has a relatively good estimation to keep it balanced. There's also the video where you pull the bag away, basically you lose track of the roll frame again. And a dynamically rigid surface, which is like there are some applications on the plane and stuff like that. And then you can move the surface like this, where it resembles what's going to happen on a boat or on a plane, and it's still going to track itself. This kind of thing. Okay, and that's it. That's true. And any questions? You have a question from Leo?
There is a question from you.
Where?
You might ask in Zoom.
Question in Zoom?
Yeah.
What's the question about?
He asked, so how many degree of freedom does it have?
Okay, we'll get back to that. Because I also don't know. That's a good question because I also don't know. Right. Any other questions? Again, like, it also took me a year to do this whole project, and I also copied a lot of work from other school. Actually, I copied most of the work from other school. I just tried to comprehend what they're saying, and it was also hard for me. Even like they probably also have this system of like the whole thing that I don't really understand, and I just want to give you guys like some insight of what you can expect in control team, and or if you are in mechanical engineering or ECE, what's going to happen if you're doing control work. And how many of you guys have taken notes today? That's a lot. Okay. Yeah, feel free to send me the notes, or if you have any questions, you can discuss it with me. And feel free to take these tips, or otherwise I have to carry back to home. Okay, you guys are free to go. Thank you.
I have a question. So who's Justin? Who? Okay, I got you. What with you?
Somehow I feel like I'm in a lot of music. Exactly. That was crazy. Well, was the like? I don't even know what to call it. The mathematics side of it. Like yeah. Once we got to algebra, like yeah, that was cool.
Adaptation. That's just advanced equilibrium. Really.
Yeah, like relating the forces to the real angles. Like that, it makes sense it would be complicated. I just don't understand how you get from A to B. But I know how to understand B and I know how to understand A.
You don't really want to be controller algorithm.
Both. Yeah. What's your name? Adi. David.